Alright, we are moving on to a new type of titration, weak acid, strong base. In the previous videos, we've been looking at strong acid titrated with strong base. Now, the weak acid strong base titration has a couple of added features to the curve, which I want to go over right now. In another video, we'll go over calculations, but I want to show you how much information we can extract from a weak acid strong base titration curve. Features of the curve, and let's emphasize it. This is going to be now weak acid titrated with a strong base. Here's our curve, or at least our axis right now. Making it fairly large, and this is going to be milliliters of the strong base added. We'll use NaOH added. Okay, and we know that this is pH. Okay, it's a weak acid, and we could pretend that that weak acid is hydrofluoric acid. So in the round bottom flask, not round bottom, Erlenmeyer flask, we have a solution, and let's say this is HF. And we know that this is considered a weak acid. It's not one of the 7 strong acids that you're asked to memorize. And then we are adding, I won't draw the burette, but we are dripping in base, and we'll use NaOH, and that's your strong base. Okay, I should have switched colors. But anyway, the pH of your weak acid is still acidic. And so before any base is added, let's put an arbitrary point there. Let's call it 2.0, or let's give it 2.1 pH. So here's the interesting part. You're dripping base into this acid, and the pH is going to rise a little bit. So we're still going to get this plateau that we've seen with the strong acid, strong base titration. But it's going to rise a little bit, okay, like that. And so that's pretty standard. And what else is standard is as you get close to the equivalence point, you'll get a rapid rise. And then it plateaus again. Okay. So here's the interesting part. Multiple interesting parts. The first thing is the equivalence point is still the inflection when you're reading it off of the graph. So the inflection is the equivalence point, and it still is when enough base is added to neutralize all the acid. Base is added to neutralize all the acid. This volume is going to be the same calculations that we did with the strong acid, strong base. No change. It doesn't matter that we're titrating into a weak acid. But that's actually, well, I shouldn't say that. I was going to say that's the only thing that doesn't change, but we'll see in just a bit. This is the equivalence volume. Actually, I do think that's the only thing that stays constant between the calculations we did with the strong acid, strong base, and the calculations we will do with the weak acid, strong base. Because this pH here, right, to calculate the pH of a weak acid, we are performing ice tables, okay, to get this number here, to get this pH. But again, let's just look at the features if you're given this graph. So let's say that this is just arbitrarily 30 milliliters. So the interesting thing is we get what's called a half equivalence. Find where it's 15, so maybe there. This is called the half equivalence, and it's very special. Okay, because at that point here, and I'll just trace there, we're going to be looking at the pHs. I totally forgot that we need to talk about the pH of the inflection point. Because that's not 7. That's maybe unusual at first because you think you're neutralizing. You're neutralizing the acid, but you don't have a neutral solution. You actually have a basic solution. And arbitrarily, I'm going to make it above 7, but let's make it 8.3. Okay. This pH is not 7 if you're doing a weak acid, strong base titration. Now, what's the reasoning for that? The reasoning for that is, we have, let's say we're doing the titration, and we have HF plus NaOH. When you have equal amounts of that, okay, let me draw the neutralization reaction, plus NaF. So we neutralize. We sequestered all of the H plus and the OH minus from these two species. Now, why? Why is the pH not pH 7? It's because we created this NaF minus. NaF minus splits up into Na plus F minus, and this is the idea where we talked about salts making an acidic solution or basic solution or neutral solution. That F minus will react with water to form an equilibrium between, give me 1 second. Let me make sure I'm doing this right. Oh, yeah. So you have here HF plus OH minus. Okay, that's a weak acid. All right, so that H is sequestered. You actually have OH minus liberated, right? Because I'm getting too much in the weeds, but NaF is a basic salt, right? Because of this idea that when you form the weak acid, that proton is sequestered and you have OH minus, extra OH minus, okay? And we don't have any more, actually we don't have any more, well, I was going to say we don't have any more acid, but we do have an acid, but it's weak. Okay, so we're not going to neutralize all of this OH minus. So that is a basic pH. Let's get back to the half equivalence. When you make these solutions as you're adding more base, what are you making actually? You have HF, right? And you add, let's say base OH minus. You're making H2O for sure, plus F minus. You know what we have here? We have a solution now of a weak acid and its conjugate base. Weak acid and its conjugate base. So this is, again, this is before equivalence. Let me just add that here. When you're before equivalence, you're not neutralizing all of the HF, so you still have weak acid in the solution. Equivalence. So now you have a mixture of weak acid and conjugate base. Henderson Hasselbalch. Okay. Because remember, Henderson Hasselbalch is used to calculate the pH of the weak of a buffer. This is a buffer. And Henderson Hasselbalch is this: pH equals pKa plus log of the conjugate. We've seen this before, and weak acid in the denominator. Okay, so here's the beauty. At half equivalence, you literally deprotonated half of that HF. If you had, for instance, 100 molecules of HF and you deprotonate half of it, you would have 50 molecules of weak acid, 50 molecules of conjugate base. These two are identical. At the half equivalence, the conjugate base concentration equals the acid concentration. What's log of 1 over 1? Log of 1 over 1 is 0. So at the half equivalence, pH equals pKa. I know that was a lot to digest. Look at the graph. We have a pH. Okay, so let's say that rise to around, I don't know, 3.0. That is the pH, but pH equals pKa. From this number right here, okay, which is at the half equivalence, the pH at half equivalence, 3.0 equals pH, but it also equals the pKa. We can solve for Ka. Right? The Ka of a weak acid is a very important number. It tells you how much it ionizes into its ionic products and its starting weak acid, the ratio. So that's cool, because let's say we have a multiple choice problem and I give you the graph and I label it, right? I put the axis markings. Well, if I ask you what is the pKa of the acid, all you have to do is find where the equivalence point is, get that number of volume, take half of it, and trace up to the curve, and then trace over to the pH. That's the pKa. Okay, so we don't see that, right? We don't see that in a strong acid, strong base titration because strong acids don't have practical Kas. We never are, we're never given a pKa of a strong acid because essentially you're close to 100% ionization. That Ka is approaching infinity because you have no acid in the denominator. All right, I don't want to belabor that point, but compare this to the strong acid, strong base titration. I actually have it here. Look how much more information we can glean from this weak acid, strong base titration versus this strong acid, strong base titration, right? We never looked at the half equivalence here, all right? Okay, so the plan is for the next two videos, we're going to answer the questions that we did for strong acid, strong base titration. These questions right here. It's complicated. It's more complicated or more challenging because we don't assume full ionization of the strong acid. We have a weak acid. And stuff like this, what is the pH? Well, what's the pH of just this acidic solution? It's right. You can't assume that that is the same concentration as H3O plus, right? You have to do an ice table. We're given Ka. Right? Remember when we did figure out the pH of an acid solution when you use a weak acid? And there are other tricks, very different, how we do these calculations versus how we did them for a strong acid versus strong acid titrated with a strong base. Okay, enough talk. This video is done. The next video, we are going to answer A and B. A and B. And then in the second video, we'll answer hopefully C, D, and E.